Two things. I'm just here to tell you that I'm going to be live later on today, after school basically. I normally aim to start about 4:30, but I end up starting about 5:30. So let's say 5:15. Okay. So this evening, after school, I'm going to be live and I'm going to be talking about the Edexcel AS Paper 2, which is tomorrow. Now, if you're not doing Edexcel, then it's still going to be useful to you. If you're not doing A-level, that's still going to be useful to you because there's still going to be lots of content which is going to be relevant for all exam boards and courses. So that's coming later live. I'm going to go through four main things that people have kind of asked me that they struggle with in their AS, which is I'm going to talk about quantum, I'm going to talk about waves and standing waves especially, and I'm going to talk about the thin lens equation, so that's like ray diagrams and stuff like that as well. And one more that I can't remember off the top of my head, which is materials. Yeah, I'm going to just talk about Young modulus as well, and making sure you can do the algebra and interpret the graphs on that. So I will see you later on. But I also challenged you, and there was a really good answer from Lindsay Murray. I challenged you to understand the Doppler ball experiment that my class were doing yesterday. And it basically goes like this. You spin a Doppler ball around and you measure the frequency of it using a microphone and Audacity on the PC. So you actually look at the waveform on the PC, and you can therefore get a time period of the wave, and you can work out the frequency of the wave. And you can therefore see a change in the wavelength, okay, or a change rather in the frequency, which is equivalent to the Doppler shift. As it's coming towards, you get a higher frequency. As it's going away, you get a lower frequency. So here's the algebra, here's what we measured, and here's the algebra. So I'll take you through that. Give me a thumbs up if this live feed is good enough for you to actually see my board there. Okay, right. So we measure the time period of the ball. So that's the circular motion of the ball. Measure the time period, how long it takes to go around one full circle. Measure the radius of the ball swinging as well, because we're going to use those two things to calculate the speed of the ball. And Doppler shift is proportional to just the difference in speed with the wave. Anyway, and then we're going to measure the frequency using Audacity of this Doppler ball when it's stationary. Call that F0. We're going to measure the frequency of the Doppler ball when it's coming towards the microphone, which we're going to call F-1. And measuring the frequency of the ball as it's going away, which we would call frequency 1. Okay, so then we're going to say Z, the redshift, is equal to the change in frequency over the frequency. And this one is for the Doppler ball when it's coming towards. So the difference between that and the actual frequency, the stationary frequency, over the frequency. So ratio, Doppler shift is like a percentage change in the frequency. And the same for the ball going away. And we're going to compare that to the speed of the Doppler ball, okay, the difference in speed of the Doppler ball over the speed of sound. So I've called that CS. Okay, that's our algebra there. Also, to work out the speed of the actual ball, we use these equations here. So the time period of circular motion is 2 pi over omega, and omega is the angular velocity. And we also know that the speed at any point of that ball in any given direction is the angular velocity times the radius. So we can do a bit of derivation to get this equation here. V, the speed, is 2 pi r over t. We measured the radius, okay, and 0.735 meters. Now, we think that's one of our main sources of uncertainty. So when you look down here at the kind of difference between our calculated values and each other, we think that's the main source of uncertainty, measuring that radius. Because when we were spinning, you're probably moving your wrist quite a lot as well. So there's quite a big uncertainty in that value. And then, so we end up with a percentage change of 2.69% in terms of the speed. So the difference in speed over the speed of sound should be a Doppler shift of about 3%. Okay, Doppler shift of about 3%. And here's our measured frequencies. So there's F0 over the top there using the thing, basically 1800 hertz. Okay, so that's about right, quite high-pitched buzzer noise. And then this is our moving away, and you can see the frequency is lower, so the pitch is lower, the wavelength is longer as it's moving away. And here's moving towards, and you can see the frequency 1900. So essentially there's a change of about 100 hertz for each of the two frequencies, whether it's coming towards or going away. And you can audibly hear that, and we measured it using the Audacity. We used as many waves as we could. We'd struggled to find really nice neat waveforms on there, but we used as many waves as we could, did the time period for all of those waves, and then boom, we went and calculated our differences, okay, between that and the stationary frequency, and we found that it's come out as about 4% there, and 5% there, and about 9% there. So it's not actually been perfect. I can see actually looking over this thing, which my students did, they've done it over the wrong flipping value. They've done it over the moving towards value, but So maybe we'll recalculate those and double check that. But the principle stands, and the main thing we were pleased with was the physics. We definitely got a Doppler shift. We definitely got higher frequency moving towards and lower frequency moving away. So we're pretty pleased with that. Well done, Lindsay, for getting your head around that really quickly. Got to ask you, Lindsay, are you a physics teacher? Because your physics is on point, really, okay? Maybe you're a physics graduate or something, so can you let me know? Just interested. And the other thing I wanted to say is in the links below, so I hope I'll see you later on for your Edexcel AS Physics kind of prep live feed. Hope I'll see you about 5-ish today. The link below is also a playlist, is also a live video I did yesterday where I went through the 2016 paper. So my advice for you, if you want to tune in later on, is go through that video, okay? Think about bits that you want to ask questions about during the live feed, okay? Because I've powered through that video. I think I did the whole paper in like 35 minutes or something like that, which is really, really quick. And therefore, you know, that's, to be honest, it's going to be difficult for you to go through. So when you go through, pause it and think about reading the algebra before you just listen to me, because you need to make sure that you actually understand that, and I really have powered through that. So if there's any kind of questions from that paper you think, oh, I just didn't get that bit about that, then you can ask them later on tonight. So I hope I'll see you guys later on tonight. I know you'll all be at school right now, but maybe you'll catch this at break time or lunchtime. Make sure you've got subscribed, make sure you've got notifications on, so that you see that tonight. All right, catch you later.